Special shout out today to all those subscribers out there. That number keeps growing. Let's keep it going. Today we are looking at day 11 review, and we have today a special guest appearance on the show to introduce our first topic. It's Mr. R.
We're going to be learning about some limits. What? That's right, Mr. Hart's bringing in those special effects.
All right, so let's take a look at our review for limits here. Thanks, Mr. Review. Let's look at limits as functions. Limits of functions. So when we do limits of functions, right, we don't have a graph, we don't have a table, we're just talking about functions. First step is plug in, right? Most of the time, if you just made up a limit off the spot, when you plug in, you're going to get an answer, and that answer is your limit. However, oftentimes we end up with getting 0 over 0. So, if we get 0 over 0, we have some strategies that we can do. Things to think about is factoring might be a way to solve it. So let's write that down. So is it possible to factor that thing? If so, do it. See if you can get something to cancel out to solve that 0 over 0 problem. Another thing you could do maybe is expand. If we have something like x plus 6 in parentheses squared, sometimes expanding that out, we'll be able to get something to drop so we can cancel out. The other one, if we see square roots, like square roots plus something, square roots minus something, hopefully by now you're saying, oh yeah, I can use the conjugate. Conjugate is another thing we could do. So those are different ways that we can be aware of and solve our limits. Again, if you get 0 over 0, that does not mean that the limit does not exist. It very well could and often does. But if we do, if we just make sure we try those different techniques, we can get x to cancel and solve it. Our second thing I want to review is continuity. At a point. We'll call that point A. If you want to prove that a function is continuous, oftentimes we're working with like piecewise functions and things like that. We have a 3-step process. This 3-step process needs to be memorized. This would be a good one for a note card. Continuity at a point A. You can put that on the front. What do we need on the back of the card to prove it? Well, 1. The limit as x goes to a of f of x must exist. So sometimes in a piecewise you have to check the left-hand limit and the right-hand limit to make sure that that limit exists. Sometimes if the function is defined everywhere except at one point, right, use that to try your limit. We just need to make sure that that limit exists. Step 2, f of a must be defined. So f of a must be defined for a function to be continuous at a point. If the limit exists and the function's defined, that's still not enough to say that it's continuous. We have to have the limit as x goes to a of f of x must equal f of a. That is our third step. Now, when we talk about when we talk about what happens, like what kind of discontinuity is it? If we fail step 1, if step 1 is a failure, then it's either going to be a jump discontinuity or a infinite discontinuity. If we pass step 1 but fail either step 2 or 3, if those are the steps that fail, then we know we have a removable discontinuity. Okay. Next, IVT. IVT is the intermediate value theorem. What would be good for a note card would be, okay, we have the IVT, we want to use the IVT to explain why f of c must equal some value, right? So here's what we need to do for that. On the back, so IVT explained. So on the back of your card, if we want to use the IVT to justify why something must be true, we need to first look at is the function continuous? So we need to state in our statement, we must state that f is continuous. If we don't know if f is continuous or not, we can't use the IVT. We have to have continuity in order to use it. 2, somewhere in your explanation, you must state the surrounding y values. So we got to state the surrounding y values. For example, you must say f of a equals 2 and f of b equals 10, for example. If you wanted to show that the c value must be f of c equals 7, you have to state those 2 surrounding values. Okay? Third step, we need to state that it must be true because of the IVT. So we need to state IVT. Okay? So that's our IVT, what we need to have in our statement. We've seen a lot of practice examples. If you go back to the IVT video, you can see it how it's written out. Next, limit definition of a derivative. Limit definition of derivative. The formula for this, remember we figured out how to find a slope of a tangent line by looking at a secant line and just shrinking the 2 points so they're right on top of each other. F prime of x is defined. So f prime of x is defined as the limit as h goes to 0 of f of x plus h minus f of x over h. And that's a way that we can solve limits. It's not a pretty way to do it, but it's a way that will work every time. It's where we get that definition from. Next. Code words for derivative. So think to yourself, what are some code words that we hear in problem prompts that tell us that we're wondering about the derivative? Well, some easy ones. F prime of x. F prime of x is the derivative of f of x. We use that notation to show derivative. Also, dy dx. That's another one. How about slope of tangent line? Anytime somebody asks for a slope of a tangent line, we know we're doing the derivative. And usually they want to know the slope of a tangent line at a specific point, so we do f prime of that point. Other things. Instantaneous rate of change. Those are all code words for derivative, and we'll learn some more as the year goes on as we progress through this. When we see those, we think derivative. Next, power rule. So we need to know the general rule for the power rule. So we want to think about a function f of x if we say a function f of x is equal to ax to the n, where a and n are any constant values, the derivative, we do the power rule by multiplying a and n together and reducing the power by 1. So f prime of x looks like this. The tricky thing for doing the power rule is oftentimes they give you a function where you need to use the power rule, but f of x is not in ax to the n form. So when we have those situations, we can follow a process here. Okay? So step 1, we want to put f of x in ax to the n form. Sometimes it's already in ax to the n form, but if it's not, that's the first thing we want to do. Make sure when you rewrite f of x, you label it still f of x. Rewriting it is not doing the derivative. Don't rewrite it and call it f prime. We want to rewrite it and still call it f. Then step 2, do the power rule. We want to do the power rule to find f prime. And sometimes if all you need to do is find f prime of x, you can stop there. But oftentimes we need to plug in a number into f prime of x. So the third thing we want to do oftentimes is rewrite f prime of x into an easy to evaluate form. We want to rewrite f prime of x to be in an easy to evaluate form. And lastly, plug in number. Not plug in hashtag, plug in number. Okay? So that's how we can do the power rule. We are going to end this video here. I have a couple more that I want to talk about, but I'll put that into the next video. Special thanks today to Mr. McGinnis for bringing the air horn and giving us a great intro to our video. I'll see you guys tomorrow.